Welcome to the pilot action of the new Metro project. The new Metro project aims to identify and support skilled workers in fourth-generation industry with an emphasis on training needs and emerging skills across Europe. As part of the project, the University of Ioannina, as a partner of the project, created a series of videos for the development of skills. This video aims to introduce the basic concepts around the Simulink module. Introduction. Simulink is essentially extending MATLAB for system modeling and simulation. The capability of modeling a nonlinear system is one of the primary advantages of Simulink. A transfer function cannot do. A second advantage is the fact that it can take on initial conditions. When a transfer function is built, the initial conditions are assumed to be zero. Simulink Start. We can start Simulink by typing the Simulink command from the MATLAB command prompt. Also, we can press the Simulink button in the following window as it appears on MATLAB. Simulink Start. The software initiates with the Simulink Start page, which can be seen below. Simulink Start. Then we click on the blank model and we see a new window that appears below. Model files. A model is a blocks collection, which represents a system. We can start a model from scratch or open existing files. Here we will show a simple model as it is given below. It is represented by a file named simple.slx. Basic components. There are two major components in Simulink, blocks and lines. Blocks are used to generate, modify, combine, output, and display signals. Lines are used to transfer signals from one block to another. Blocks. There is a library that contains a number of block classes. Sources, utilized to generate signals. Sinks, used to output or display signals. Continuous time system components, continuous transfer functions, state space models, bit controllers, etc. Discrete, linear, discrete time system components, discrete transfer functions, discrete state space models, etc. Math operations includes a plethora of math operations. Ports and subsystems, handy blocks to construct a system. Blocks include 0 to a number of input terminals and 0 to a number output terminals. Unused input terminals can be shown using a small open triangle. Unused output terminals can be shown using a small triangular point. The block shown in the image includes an unused input terminal and an unused output terminal. Lines. Lines transmit signals towards the direction shown by the arrow. Lines must always transmit signals from one to another block. From output terminal to the input terminal. It is prohibited for lines to inject a signal into another line. Lines must be combined through the use of a block, such as a summing junction. A signal can be either a scalar signal or a vector signal. For single input, single output, SISO, systems, scalar signals are generally used. For multi-input, multi-output, MIMO, systems, vector signals are often used, consisting of two or more scalar signals. The lines used to transmit scalar and vector signals are identical. The type of signal carried by a line is determined by the blocks on either end of the line. Lines. An exception is a line that can tap off of another line, splitting the signal to each of two destination blocks, as shown in the next slide. Simple example. The model we call simple comprises three blocks: step, transfer function and scope, as we can see in the figure below. Simple example. The step is a source block from which a step input signal comes from. This signal is transferred given a line towards the direction shown by the arrow. The signal results to the transfer function continuous block. The transfer function block modifies its input signal and outputs a new signal on a line to the scope. The scope is a sync block used to display a signal much like an oscilloscope. There are many more types of blocks available in Simulink. Simple example. Altering blocks. If we double-click on a block we can change its properties. As we can see with the transfer function block of the simple model in the figure. This dialog box includes fields for the numerator and the denominator of the transfer function. By entering a vector containing the coefficients of the desired numerator or denominator polynomial, the transfer function that we want can be inputted. Simple example. For example, to alter the denominator to s squared plus 2s plus 4, we have to type in the denominator field the following and close the window. Then we will have the following change in the simple model, which essentially constitutes the alteration in the transfer function of the model. Simple example. The step block as the transfer function can be double-clicked, bringing up the dialog box in the figure. The default parameters in this dialog box create a step function occurring at time equals 1 second, from the level 0 to the level of 1, a unit step at t equals 1. Each of these parameters can be changed. Again, we have to close this dialog to continue. Simple example. We can also double-click the scope block, which brings up the oscilloscope window of the image. This window is essentially active when we run simulations. Essentially, the signal which is directed into the scope is displayed. Simulations. For the simulation, we will use the previous modification in the simple model, which is shown below. Simulations. Initially, we have to open the scope window as we have seen previously by double-clicking it. In order to commence the simulation, we have to press Run from the simulation menu or click the play button, which resides at the top of the screen. An example is shown in the accompanying figure. Simulations. The output of the simulation as it appears in the scope window is given in the figure below. Simulations. The step response does not commence until t equals 1. We can alter that if we double-click on the step block. If we change the parameters of the system and simulate the system again by double-clicking on the transfer function block and change the denominator to 1/2400. We run the simulation again and we see the following output in the scope window. Simulations. The transfer function has a very fast response. It is thus compressed into a very narrow part of the scope window. This does not constitute a problem with the scope, but with the simulation itself. We performed a simulation of the system for 10 seconds even though the system reached the steady state close after 1 second. Simulations. In order to make it right, we are required to modify the parameters of the simulation. In the model window, we select the model configuration parameters which resides in the simulation menu. We will see the dialog box in the figure. Simulations. In the dialog box there is a number of simulation parameters. We only care about the start and stop times, which tell Simulink the period of the simulation. If we change start time from 0.0 to 0.8 and stop time from 10.0 to 2.0, we will have tighter bounds of the system starting and settling. If we run the simulation again, the scope window will make more sense, since the time will capture the system operation until it settles without necessary unused time. Systems building. Here we will show how to build the steps of building the system of the figure below using Simulink's block libraries. Systems building, gathering blocks. We create a new model by clicking New from the File menu. We will see a blank window. Then we click on the Tools tab and select Library Browser. After we click on the Sources listing in the Library Browser, this will show the Sources block library. Note that sources are used to create signals. Systems building, gathering blocks. We drag and drop the step block from the Sources window into Model window. We click on the Math Operations listing in the main window. From this library, drag and drop a sum and gain block into the window. We click on the Continuous listing in the main window. Initially, we drag and drop a controller block in the window from the same library, drag a transfer function block in the window, thereby we click on the Sinks listing in the main window. Drag the scope block. Note that the order that we place the blocks is given from left to right as they are described. Systems building, modifying blocks. We double-click on the sum block. We desire that the second input to be subtracted, hence we enter plus into the list of signs field. We double-click the gain block. Change the gain to 2.5. We double-click the PID controller block and change the proportional gain to 1 and the integral gain to 2. We double-click the transfer function block. Leave the numerator, 1, but change the denominator to 124. Then we change the PID controller and transfer function block names by double-clicking on the names and use the Pi controller and plant respectively. Systems building, connecting blocks with lines. Drag the mouse from the output terminal of the step block to the positive input of the sum input. The line should have a filled arrowhead. In the case that the arrowhead is open and red, it is not connected. Draw a line connecting the sum block output to the gain input. Then draw a line from the gain to the Pi controller, a line from the Pi controller to the plant, and a line from the plant to the scope. The line which is left for last is the feedback signal connecting the output of the plant to the negative input of the sum block. This line loops around and does not simply follow the right-angled route, hence it needs to be drawn in several phases. Also, there is no output terminal to start from, so the line has to tap off of an existing line. Drag a line off the negative portion of the sum block straight down and release the mouse so the line is incomplete. From the end point of this line, click and drag to the line between the plant and the scope. Finally, add labels to the signals by double-clicking where we want them to be. Systems building, result. We have again the following result. Conclusions. Here we showed how to use the Simulink tool. We showed a simple example and some stages of the tool's operations. Then we discussed how to build a more complex system. Acknowledgement. This presentation is based on the following tutorial. Thank you for your attention.